So the first speaker for today and for the whole semester is Professor Scott Zimmerman from The Ohio State University. He will deliver a series of 2 talks, and the title of the talk is Extending Curves in Metric Spaces. Part 1, Smooth Curves in Carnot groups.
Thank you very much. I very much appreciate the invitation, the opportunity to give the talk here. I'm actually going to turn my mic down a little bit. There we go. I don't want to destroy whoever's watching this as speakers, because I'm a very loud talker. All right. So, and thank you all for coming. What I'm going to talk about is work that I've done over the past decade. If you've seen me give a talk before, you've probably seen me talk about some of this stuff. So, but there is plenty of new in this talk as well. So don't be too bored. All right. So let's start. So Whitney extension theorem. This is what part of my dissertation work was on the Whitney extension theorem. And the classical Whitney extension theorem tells us something like, suppose you've got a continuous function defined on some, say, compact set, right? And then you've also got a collection of other continuous functions, f alpha, defined on that compact set. And how you want to think about that other data that we have is those are like what the vector fields should look like, what the gradient fields should look like for our function f, right? So f is defined on a compact set. I made a nice looking compact set here. We can see its graph, but you can make your compact set be as nasty as you want, or even actually any closed set. I'm sticking to compact for niceness here, but any closed set. Anyway, when can we extend this picture smoothly? When can we interpolate the data here smoothly? In other words, when is there a CM function, capital F, so that when I restrict capital F to my compact set, I get the original graph I pictured, and all the partial derivatives of F match up with this family F alpha, right? So what I'm doing is I'm assigning values of the function, I'm assigning derivative values of the function, I've got some data here, and I want to know when can I fill in the gaps nicely. There it is. When can I fill in the gaps nicely, like that picture? All right. So what Whitney proved, the answer to this question is that you have a CM extension if and only if Taylor's theorem is true. What's that mean? Well, we know if you have a CM function, then you have to have Taylor's theorem, right? You have to have something about these Taylor polynomials vanishing quickly enough. But it turns out, don't try to parse this, but here I just decided to throw the statement up here. If you know that some sort of Taylor polynomial approximation converges fast enough, then you know you have a smooth extension. That's what you need to be true about your data. Okay, so that's the idea. That's the Whitney extension theorem. Okay, so let's think about this in the context that I'm going to think about it, where we have, thinking about extensions. I'm just going to walk up here. Imagine you're a drone pilot in training. I said this to a few of you, but not everybody. If you hate AI-generated pictures, I apologize in advance. I used them for humor purposes. That was it. So you're a drone pilot in training. This is AI's best attempt at pulling this is Hostler Whitney from his Wikipedia page. And this is, what's his name? The guy from Full Metal Jacket and then everything else. So yelling at him. He's a drone pilot. Hostler Whitney's trying to learn how to fly a drone. And he is handed some flight plans that he needs to fly. And so the data he's given is where he needs to be at every time. But Whitney's also told maybe at certain times what his altitude needs to be and also what his airspeed needs to be. And maybe he has information about second derivatives and third derivatives and fourth derivatives. You know, he has all kinds of information about this flight plan. Well, what Whitney's extension theorem tells us is whether or not this flight plan is feasible. right? Whether or not I can actually fly this flight plan, right? Can I actually fly this flight? Here's one that doesn't make sense. Instantaneously change your velocity, right? When you're flying a quadcopter drone, that doesn't make sense. He doesn't have some like quantum particle he's flying around. He's flying a quadcopter drone. He can't instantaneously change his velocity. Somewhere, we know that the velocity must be equal to 0, right? When you're turning around, we teach that in calculus. So what I'm going to do is I'm going to change the question a little bit. Now you're a fixed-wing drone pilot in training. Piotr's not here. This is the picture from his poster, so I'm allowed to, he volunteered that to be on the internet, so there's nothing wrong with using that picture. So now we're flying a fixed-wing drone pilot. And the question is, Piotr's handed the same flight pattern. When is this path feasible? Can you take the dotted lines and connect them to a smooth line? The problem is, not problem, or the difference is, in this scenario, your motion is controlled by the data that you have. Meaning, with a fixed wing, let's say, F.C. Bailey, I think was his name. F.C. Bailey, I think that's the name of the guy from Full Metal Jacket. Let's say he tells Hassler Whitney, fly straight up. No problem. Whitney can do that. If he tells Piotr, fly straight up, that's not going to happen. Right? Because you can't just, from a standstill, you can't just this isn't one of those VTOL vertical takeoff and landing planes, right? You can't just tilt back and fly straight up. You have to take off first. So there's something different about what you're allowed to do when you have a fixed wing drone versus a quadcopter drone. Another AI generated picture. How do you drive to the roof of a parking garage? The much simpler explanation, you don't do that. What you do is you drive up the ramp, right? This very American picture here. You drive up, the spiral ramp. The only way you're going to get to the roof is if you're driving up one of those, if you're on the ramp, right? That's the only way to move up or down. So we describe motion in RN using vector fields, right? So the way we can control motion, we can describe these scenarios where you're only allowed to move certain directions. One way we do this is we restrict our attention to a subspace of vector fields. And we assume that they vary smoothly, and we make some nice, what's called bracket generating assumptions on these vector fields and things like that. But the main idea is that we're taking our regular tangent space at every point, which is in this picture R3, and we're restricting our attention to a plane within that tangent space, right? And what we're saying is Hassler Whitney can fly whatever direction he wants. Piotr can only fly tangent to certain planes. Right? This is not an exact description of the airplane setting or the drone setting, but this is just bring your mind there. Okay. So what's a little bit more accurate description is, let me throw some math into this. We have somebody walking. Right? Someone's trying to walk around a room and they want to get out of this door. Right? I'm standing right here. I want to get out the door, and let's say one other piece of information that I care about is the direction that I'm facing. Right? So I have 3 motions I can combine together, which allow me to get out the door. One, I'm calling it V1, is I can rotate myself. Right? If you're being very careful, I may have some signs screwed up somewhere, so I apologize in advance. But anyway, V1 is me rotating myself. I'm allowed to change the direction I'm facing, right? When I'm walking, that's not a big deal, but that's okay. Maybe I'm facing this way. Let's say I want to make sure I'm getting out. I'm standing right in front of the camera. I'm sorry. Let's say I want to get out the door facing a certain direction. So I care about the direction I'm facing, right? I'm also allowed to walk straight forward. I'm also allowed to strafe side to side, and then anything I do is some combination of those, right? I can walk diagonally, and what I'm doing is I'm combining my forward and my sideways motion. So if I describe these actual vector fields, what I get is, I can change my angle, I can walk in the direction I'm facing, or I can walk orthogonal to the direction I'm facing. That's what these vector fields describe. And so any motion I can make is some combination of these three vectors. Okay? If I'm sitting on a unicycle, that changes things, right? I'm only allowed, in this case, two motions and any linear combination of those two motions. I'm not good at riding a unicycle. I can't take a unicycle and hop to the side on it. I'm not going to be able to do that. What I can do is I can roll the direction that I'm facing, or I can rotate myself. I only have these two vector fields to work with. But no matter where I am, I can still, it's not, I forgot to include that picture here. Oh well. No matter where I am, if you think about it for a second, imagine me at any point in this room sitting on a unicycle, I can still make it out the door, right? There's still some path. I only need two vector fields of directions to get out the door. I don't need all three. Three was too many. That was being a little too greedy. Is the screen being shared right now on the recording as well, Tomasz? If I was to pull up a website?
Probably the website will appear on the...
Okay, let me, is that okay if I do it? Okay, I don't want to do anything I'm not supposed to here. Zimmerman, I meant to pull this up ahead of time. ZimmermanMath.com, apps. All right, this is another thing I've been taking advantage of my free Gemini Pro subscription. Here's a person walking around, right? You can go forward and backwards. They can move side to side, or they can rotate their body, right? And really, I should switch the X and the Y there. I need to update that. If I want to get to that white circle target facing the direction indicated, I can do that just by walking in a straight line and kind of, that's not how you would probably do it, but that's an efficient way. If you're trying to be really efficient, you'd walk backwards to try and get to that target. However, if I'm on a unicycle, I no longer can strafe side to side. All I'm allowed to do is rotate and move, but no matter where I am and no matter where I'm facing, I can still, there we go, not what I meant to do. I can still get to the target. Stop it. Stop being difficult. I know. Whatever. I know there's a way to do it. I just can't wrap my brain around it right now. But there's, wherever I am, I can either roll forward and backwards and rotate myself and get to where I need to be. And you can see that these are sort of, this is actually not the most optimal. My kids love playing with this. They like driving the dude really far away and then pressing the button and just watching him go back. No matter where you are, you can still get to the right spot facing the right direction. Okay. So that was the wrong button. There we go. That's the wrong button. Wait, I got it. There we go. I can recognize it by pictures eventually. All right, so the way that we mathematically describe this idea of combining these two vectors together to be able to get any direction I want to go is more than just talking about linear combinations of them. The idea is that I can combine these vectors by using what's called the Lie bracket of the vectors. And it's defined in this way, but essentially what it does is what this calculation here does is it measures how far these two vectors are from commuting with one another, right? It's called the commutator in linear algebra when you're dealing with matrices. Same idea here with vector fields. This commutator here measures how far apart they are from commuting. If these vector fields commuted with one another, meaning I walk along, what I mean by that, I should explain that. Walk along one a tiny bit, walk along the other a tiny bit, walk backwards along one, walk backwards along the other, where do I end up? If I end up right where I started, those vector fields commute. If I end up somewhere else, they don't commute, right? So that's this idea of v1, v2 minus v2, v1. Turns out if you make that computation here, you get that third vector field that we were missing. So you can actually move any direction by combining these two motions in a certain way, right? If I'm standing here and I wanted to end up over here, right, on a unicycle, I could either hop if I was good, or I could move forward, rotate a little bit, move backwards, and then rotate back to where I started. And now I've moved to the left, right? I've combined those two motions in a certain way. So bringing this, back to the title of the talk, Carnot groups, what if we think about our Euclidean space as split into layers almost, as they're typically referred to. So the first layer, the second layer, the third layer, n1. The second layer has dimension n2, et cetera, et cetera. We can define at every point an n1 dimensional space of vector fields. And so, for example, planes at every point in R3, right? Do I have that? And the only paths we're going to consider are those that lie tangent to the subspaces that you see in this picture. And I'm going to talk about this more in a minute with a much more concrete example. Here is the general definition of a Carnot group as a Euclidean space, right? You can describe these algebraically in general, but it turns out they're all equivalent in the way that you want them to be equivalent, right? Lie group isomorphisms to this format. But the idea is that when I'm saying Carnot group, because there really is a group operation we're talking about. You can talk about Lie theory here. You can talk about the Lie groups. I'm talking about Lie brackets, that kind of stuff. So there is Lie theory happening here. I'm brushing over a lot of that just to save time, but there's a lot of cool stuff happening in the background here. The translation of number 2 right here is we can move any direction we want by combining movements in only the first n1 directions. You only look at motion through these planes, and you can get wherever you want in R3, turns out. Okay? So I'll talk more about that in a minute. And then when I'm talking about moving through space, I'm just talking about curves. Let's just talk about a smooth curve. You can be more general than that. You can restrict to absolutely continuous curves so they're differentiable almost everywhere and stuff. But let's just look at smooth curves for now. A smooth curve is horizontal if its derivative lies in the span of those vectors. In other words, if you're on your unicycle, the only directions I'm allowed to move are using the V1, V2 combinations, but that's good enough to be able to get me out the door. Right? I'm only moving using the rolling forward and backwards and rotating options. I'm not hopping side to side. And it turns out that you could define a metric, and this is the kind of the meat of kind of how I'm viewing this seminar, not seminar, but this semester, as like kind of geometry on metric spaces, because that's what I like to study. We can turn any Carnot group into a metric space by minimizing over lengths of curves. In the same way that we make, you take a sphere and you want to know the distance between 2 points, look at all the paths between them, minimize those. You can do the same thing in a Carnot group. All right. Any questions so far? I know I'm not supposed to pause for questions in the middle, but. All right. So my concrete example is the Heisenberg group. I'm going to go a little bit faster than I normally do through this part because I've already talked about a lot of this stuff in the general case, but here's that general case in a very concrete setting. So let's make everything very official here. Take R3, regular R3. At every point, we're going to define capital X to be pointing in the X direction and then tilted down or up based on what my Y coordinate is. So I'm pointing in the X direction. As I walk in the Y direction, this starts to tilt down. Yeah. Capital Y is pointing in the Y direction. As I walk in the X direction, this starts to tilt up. And so if I move some combination of those, I get some combination of tiltings. I think I messed my fingers up there, but whatever. There's an uglier picture of that. If you want a beautiful picture, let's go back to this. This is fun. F11. Shortcuts are different. All right. Here is the vector field X that I was describing. They're like little cone arrow thingies. There's that vector field X as if I'm standing, if I'm walking along, the X direction, it's always pointing in the X direction. But as I move away from the X-axis, this starts to tilt in the Y direction. Here's the vector field Y. As I move away from the Y-axis, the vectors start to tilt up or down based on its X-coordinate. Here are those planes that I showed you in the previous part. Fun stuff. These are all on my website if anybody wants to steal these. I don't care. Feel free to steal them. Here's an easier picture. Let's only look at the z equals 0 planes. There they are. There's the planes. Notice at the origin, the plane is just the xy plane. But as I move around, they start to tilt based on what my coordinates are, right? And so the idea is I'm only allowed to move tangent to these planes. This is what an admissible curve looks like in this setting. A Legendrian curve or a horizontal curve, as I've defined it in this talk. A horizontal curve looks like this. And if I want to get real fun, where is it? Uncheck that, click this button, and now you can fly. There we are, flying along. And if you notice, as we pass near those planes, we're pretty much tangent to those planes. No, don't applaud me. Applaud Google Gemini. It was like a Saturday when I was playing with my kids, and in between playing with my kids, I'd be like, no, don't do it that way. And I'd have it, think in the background while I'm playing with Legos, and I'd come back and look at the horrible program it created, and then I had to, it was like a 6-hour conversation. I ran out of OSU allowed Google or Gemini Pro credits to be able to talk to this thing. I had to do it on Sunday as well. This one and the the unicycle one were the hardest. Anyway, we'll get to the other fun stuff later. I'm not going to even talk about that. So the sub-Riemannian, that's what's referred to. I don't even know if I've used that word yet. I haven't. This is what's called sub-Riemann. This is an example of sub-Riemannian geometry. Riemannian, like the sphere, like being on a torus, that kind of thing. Sub-Riemannian just refers to the fact that we are looking at in my mind, we're looking at a subspace of the tangent space, right? I say here at the bottom, we choose Riemannian metrics that make capital X, capital Y, and partial Z orthogonal. What I'm going to do is I'm just going to say, like, okay, if I'm sitting in this plane, I have a vector that's in this plane. How do I talk about the length of that vector? I'm going to define a metric from the language of differential geometry metric on each of these planes in order to be able to talk about the lengths of curves there. Right? And then I can talk about lengths of vectors there. Then I can talk about lengths of curves from that. Okay. I like doing this kind of talk just because it's like, I want other people to be interested in the things that I'm interested in, because like, I didn't expect to get to only publish papers that have Carnot group or Heisenberg group in the title, but apparently that's all I do. So my talk on Friday is going to be, it was supposed to be a paper in the Heisenberg group, and then it turns out that the result holds in much more generality. So we didn't even talk about, I think we threw in like, an example of this is the Heisenberg group. So that was the only time we talked about it in that paper. Anyway, there is a whole Lie group structure we can put on this. You can approach this from the theory, from the world of Lie theory. The left invariant vector fields of this group operation are those capital X and capital Y that we were talking about, and capital Z, but we're only going to care about capital X and Y. And yeah, that's the same picture. Don't know why I threw that in there. The dilation is a group automorphism, meaning if you take a point and you dilate it in this specific way, where in the x and y direction things happen linearly, in the vertical direction things are squared, that's a group operation on this space. Things happen really, it maintains this group operation. It maintains the whole differential structure of our space, so things don't change. So it gives us this really nice structure. Okay. And what's a horizontal curve? That's a horizontal curve. These are the directions we're allowed to move through space. You can see the planes now. This is an ugly picture, but you can kind of see, here it is tangent to that plane. Cool. Okay. I'm good. Whitney extensions in the Heisenberg group. Again, if you've seen me talk about this before, I apologize. I know I see faces in the crowd that I haven't seen in many years, and I'm still giving this talk. What would a Whitney-type theorem look like into the Heisenberg group? Well, what would that mean? That means I have parts of a curve, right? And I have, I left something out. I have parts of a curve, but I also had the extra data where, let's say I know the extra, like the velocities and the accelerations and stuff like that, right? I have a flight plan. I have parts of a flight plan. I don't have a full flight plan. Whitney told us when a smooth curve exists that can fill in the data, the question is, when do you have a horizontal smooth curve? So here's the scenario. There we go. That was an extra slide I didn't need. Whitney told us that if you think about the simplest case, the C1 case, you have a C1 extension if and only if you have uniform convergence of the difference quotients, right? Imagine what the difference quotients should be, right? You have, starting at a point, you step forward a little bit, and you want to make sure that point where it ended up lines up correctly with what the velocity says it should be, right? That's what a difference quotient tells you. It says you started at a point, and I fired my cannonball along this velocity vector. I better end up very close to the next point on gamma. I'm not wording that correctly, but hopefully you know what I'm saying. Yeah. It turns out that in Carnot groups, specifically in the Heisenberg group, there's a very natural generalization of the difference quotient, or the regular derivative, sorry, to what's called the Ponshu derivative. And the Ponshu derivative satisfies a Rademacher theorem. Lipschitz maps between Carnot groups are Ponshu differentiable almost everywhere. And so it's a very natural notion. Turns out it's still a difference quotient. F of x plus h minus f of x divided by h. This is that dilation thing. This is just a difference quotient using the language of our Lie group. It turns out you can still classify C1 extensions. That's an old reference right there. You can still classify C1 extensions, C1 horizontal extensions in terms of uniform convergence of some difference quotient, right? So this very natural Whitney idea extends very naturally to curves in the Heisenberg group. So what does this tell us? Here are just a list of other results that have happened in the past decade related to this. There is a CM horizontal extension classification result. It relates to more Taylor-like things that don't have, as far as we can tell, a nice geometric interpretation. No one has yet discovered a nice geometric interpretation. That was done with Andrea Pinamonti and Gareth Spate. And by no one has yet discovered, I'm not pretending like there are people digging it deeply into this besides me. So yeah, my ego's not that big. We can do a C infinity with horizontal smooth extensions if you refer to these Taylor-like polynomials. There is a finiteness, I clicked too many times. There's a finiteness principle. If you're familiar with the work of Charles Pfefferman on the classical Whitney extension problem, you'll know what that means. If not, that's okay. It's just saying that stuff that works in Euclidean space also works into the Heisenberg group in a very natural way. And then we also have these, we have these Lucin type approximations, and that's what I'm going to focus the rest of my talk on, is the idea of these Lucin approximations. I'll explain what those are. First, let me tell you some results, then I'll tell you I'll define it. So don't worry, it'll make sense when we get there. In my original paper, and also Gareth in the same year, totally independently, realized that there are C1 horizontal Lucin approximations. Whatever that means, I will explain it in a minute. Funny story about this is I was presenting this result at a conference the very first time I was going to meet Gareth, and I was terrified to meet him because I thought he was going to be angry that he and I had proved the same thing, and I was a grad student at the time, I didn't know. And if you've ever met Gareth, you'll know that he is possibly one of the nicest people in the world, and like could never be mad at anybody. So it's just funny that has happened. And now we work all the time together on stuff. So happy ending. You have higher order Lucin approximations as well, like Cm and C infinity. Also, you need something about L1 differentiability of functions, but yeah. All right. So let's talk about something that is of interest, I hope, to geometric measure theorists, geometric analysts, this idea of rectifiability. And what can we say about rectifiable sets in Carnot groups based on the results that I've just discussed? Okay? So we're going to say a set in a metric space is blank rectifiable by curves. So if you tuned out and didn't care about any of that Whitney stuff, you don't need it for this part. So you can tune back in for rectifiability. I'll refer to it a few times, but it's not going to be super important. Is blank rectifiable? I'm going to say by curves, because when you're in a general metric space, having curves covering your set versus arbitrary sets covering your set they're different scenarios, but this is what we need in this scenario. So let's just bear with me for now. A set in a metric space is something rectifiable by curves if there is a family of that thing curves such that the measure, the one-dimensional Hausdorff measure of take your set E, throw out the image, throw out the curve, all those curves that you just drew, that remaining set had better have measure 0. This is, so fill in the blank with some nice property. So for metric spaces, usually we talk about Lipschitz rectifiability, right? Because Lipschitz is the natural thing. That's the natural family of curves to talk about in metric spaces. So I'll show pictures on the next slide. What this means is that almost all of our set E can be seen by these kinds of curves, by Lipschitz curves. It's this generalization of manifolds, right? Manifolds are sets that we can cover with smooth charts. Here we have sets that we can cover with almost smooth Lipschitz charts almost everywhere. Almost is a very powerful word in geometric measure theory. What's up?
This family, how big could it be?
Countable. We're going to talk about countable families. Yes. Yeah. That I should be integers, or natural numbers. Thank you. And a set E is on the opposite end of the spectrum. A set is purely blank, let's say Lipschitz, unrectifiable, we'll say by curves, if the one-dimensional measure of E intersected with any curve is 0. So in other words, for any Lipschitz curve or any smooth curve or any whatever curve you want, E doesn't see it, right? So they're kind of opposite ends of the spectrum. Rectifiable means everything can be seen by, say, Lipschitz curve. Every part of your set almost all of your set can be seen by Lipschitz curves. But purely unrectifiable means almost none of your set can be seen by Lipschitz curves. Okay? Oh, there we go. I should say not none of E, but almost none of E. Sorry about that. All right, the top pages, the top pictures are not AI generated. Their image credit is Nora and Lydia Zimmerman. I know that's one rectifiable because I saw my kids draw it, and they did it in finite time. So this is an example of a one rectifiable set because it can be covered by curves, imagining those are one-dimensional curves. So that one rectifiable sets don't have to, these aren't filled in. They're scribbles. I didn't use a filling tool in Paint. This is actual scribbles there, and they drew this in finite time, so I know that this is a one rectifiable sets. The regular Sierpinski carpet, the Van Gogh snowflake, these are purely one unrectifiable sets. The reason they're purely one unrectifiable is because if you tried to put a finite length curve in here, you can't do it. Every curve in here has to be infinite length, right? On the Van Gogh snowflake's the most obvious example of that. If you try to draw a curve around that covers up any meaningful part of this picture, it's going to have to be infinitely long. There's no way you can get a Lipschitz curve on the interval from 0 to 1. A really interesting example is Carnot's four-corner dust, which is defined by you start with a square, you remove, you keep start with your square, cut it into 16 pieces, 4 by 4. Keep the upper left, upper right, lower left, lower right. Do the same on the remaining squares. Do it again, do it again. And what remains has Hausdorff dimension 1, but it is purely one unrectifiable. It won't see, from in the sense of the one-dimensional Hausdorff measure, it doesn't see Lipschitz curves. So that's a very interesting example. These guys have dimension larger than 1. Here's, if you kept going with this, dimension 1, but doesn't see any Lipschitz curves. So very interesting. Okay. So what's very well known, you can find it if you dig through Federer's book, in Euclidean space, Lipschitz rectifiability and C1 rectifiability are equivalent. Why am I bringing this up? Because this follows from the Whitney extension theorem, right? You apply, start with your what am I saying? Take your set. You know what? I'm going to talk about that in a second. I'll talk about why that is in a second. Let me talk about Lucid approximations before I talk about that. The question is, what about Carnot groups? What does rectifiability look like in Carnot groups? And it's very well known and well studied that for sets with dimension larger than 1, so for example surfaces, that kind of thing, the notions of C1 rectifiability and Lipschitz rectifiability, I shouldn't even say that the notion. There are multiple different ways of defining this idea of Lipschitz rectifiability in even in the Heisenberg group, in the simplest non-abelian example. So for higher dimensional sets, you have multiple different ways of talking about Lipschitz rectifiability. I don't claim to know too much about that, so please don't ask questions about that. There are other people in this room that I'm sure know more about that than I do. However, in the one-dimensional case, usually things are easy, right? In the one-dimensional case, when you're talking about curves, typically things are easier there. So the question is Lipschitz rectifiability and C1, say, horizontal rectifiability, the same thing? Can I cover, if I have a set that I can cover with Lipschitz curves, can I also cover it with smooth horizontal curves? That's the question. And vice versa. If I have a set that I can cover with smooth horizontal curves, can I cover it with Lipschitz curves? Well, yeah, because they're smooth horizontal. So one direction's easy. The other direction, not so much. So for sets with dimension greater than 1, this has been well studied, and the notions of rectifiability are all very, very different. And I'm not going to talk about that part of it any further. The real meat behind what's going on here is the idea of a Lucid approximation. So here's what it says in a picture. Say you have a Lipschitz curve in Rn. Very, very, very jagged. For any epsilon you pick, you can shave off the corners of this Lipschitz curve, and create a C1 curve so that the times in the domain where these curves are not the same is as small as you want it to be. You can shave off the corners, but you want your smallness to be even smaller? Fine, shave even less off. Oh, I want my smallness to be even smaller? Fine, I shaved even less off. I can always get a C1 curve, right? The derivative is going to blow up at the smaller epsilon gets, but I'm always able to do it. I can always shave off a corner. So translation, every Lipschitz curve in Rn is mostly smooth. Okay? Turns out in the Heisenberg group, it still works. If you have a Lipschitz curve in the Heisenberg group, then for every epsilon greater than 0, there is a C1 horizontal. So the C1h means C1 horizontal curve. So that this, the difference, the set of times where they're different has measure as small as you want. Same kind of, so it's this picture again. This picture again works. If this was a horizontal curve, it again works in the Heisenberg group. Great. Every Lipschitz curve in H is mostly smooth. What about more complicated Carnot groups? So I'm not going to define any of these just so I don't get into the nitty-gritty weeds. This is the part of the talk where it's like, if you already know what I'm talking about, great. If you don't, bear with me. Just understand that here E is what's called the Engel group. It's one step more complicated than the Heisenberg group. It's the second jet space. If you have a Lipschitz curve, it turns out that if you have a Lipschitz curve in the Engel group, then that doesn't make sense. Forget this first sentence. That first sentence shouldn't be there. I should have deleted that first sentence. Start here. For every epsilon, there is a Lipschitz curve so that the set of times where this Lipschitz curve differs from a smooth curve is almost all the set, and I say almost all not in the correct way of saying almost all, is most of the set for as most as you want it to be, right? The set of, another way to think about this is the set of times where they're the same is less than epsilon, right? There, you can create a really, really ugly curve like that in the Engel group. Here it is in, these are the coordinates x1, x2, x4, whatever. You can create a Lipschitz curve that is mostly non-smooth. Okay, can I have like 1 minute? Oh, okay, okay, cool. Okay, I won't take the whole 10 minutes. Don't worry. Is there, I'm kidding. Is there a Lipschitz curve that is almost never smooth? So what this example shows me is I can create a Lipschitz curve so that when, like, no matter what smallness you pick, I can make sure that I create, okay, let's say that again. No matter what smallness you pick, I can always create a picture like this, or Gareth can always create a picture like this that differs from a smooth curve up to a set of measure epsilon. The question is, can you create a Lipschitz curve that where the measure of the set where it overlaps with a smooth curve is 0, where the measure of the set where they're different is the whole time interval, right? Is that possible? And it turns out the answer is no, surprisingly. In the Engel group, you can't do it. If you have a Lipschitz curve, then you can always come up with some smooth horizontal curve that sees the time domain somewhere. It sees it somewhere. The measure of the overlap between that Lipschitz curve and the C1h curve has to be positive, which is I thought was surprising. I just figured you could take Gareth's example, and Gareth and I figured you could take Gareth's example and just like iterate it a lot, and eventually you get 0, right? If it works for every epsilon, it should work for 0, but it doesn't. You can't just iterate it forever, and this is due to some geometric property. So every Lipschitz curve in E is smooth somewhere. So is there a Lipschitz curve in some Carnot group where this is possible? And why is this interesting? And this gets back to the idea of rectifiability. If such a Lipschitz curve exists, then the image of this curve would be C1h purely unrectifiable. Meaning you can come up with, if such a curve exists, then you can come up with a Lipschitz curve whose image is purely C1H unrectifiable. Meaning Lipschitz rectifiability and C1H rectifiability are very, 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 very different, right? They can't be similar at all. And the answer is, I'm going to skip over that. The answer is yes, you can. So I say 2026 because that the preprints on archive, is it? Yes. Still submitted. But there is a Lipschitz curve into what's called the free Carnot group of step 3 with 2 generators, also called the Carton group, so that every smooth curve you pick sees their domains where they overlap has measure 0. They are different almost everywhere in the domain. That's what it's saying. There is a Lipschitz curve so that no matter what C1 horizontal curve you pick, they're going to be different in almost everywhere. So what I want to really do is just show off one more thing. And so this is fun just for you, because pictures are fun. Here's what the curve looks like. Again, thank you to Gemini for this. This was the, here's what the curve looks like at several iterations. Notice that dot moving along the curve. You can see the dot moving along the curve. It's moving at constant speed, even though it looks like it's flying when it gets to those like other directions. That's just what I'm visualizing right now is the coordinates x1, x2, x5. So I've got x1 going one way, x2 going another way, and x5 in the vertical direction. So what's happening is moving in the x5 direction is like polynomial motion, but from the perspective of a Carnot group, this is moving at constant speed. So here, see perturbations. This is the fun thing. Oh, follow camera. There we go. Right now, I'm flying along the curve, and what you weren't able to see is that there are little kind of fractal back and forth things happening at really tiny intervals along this curve. And now we're going to get to the end of something, and now it's going to go, So it's essentially what this construction is. It's like a Van Koch snowflake. It's all we're doing here. We're taking sort of what we called staircase functions and iterating those over and over again. And so now as we fly back down, we get this crazy back and forth fractal motion. But it's happening at such small scales you can't see it unless you're on the... This thing is moving at a speed of 0.005. Very, very, very slowly, where 1 is the normal speed. Anyway, that's all I wanted to share. The very last bit is, what's my white whale? What happens for surfaces? This whole talk was about curves. What happens for surfaces in the Heisenberg group? No idea. This was the question that got me on there. Piotr Hajwasz is my PhD advisor. He asked me this question like when we started working together, and 0 progress has been made since then. So like, besides all the curve, besides the last hour, besides the last decade of my life, 0 progress has been made. So we know a lot about curves, but with surfaces, the problem is things get really weird when you talk about surfaces. For example, in the regular Heisenberg group that I was talking about, there do not exist smooth horizontal surfaces. You need to talk about higher dimensional Heisenberg groups for that to even make sense, because there's topological stuff that gets in the way. I say this is a proposition because it's very simple to see that if you have a C1 horizontal extension, then you have uniform convergence of the Pan-Su difference quotients. I shouldn't say it. It's very easy to see in the Heisenberg group, not in general Carnot groups. Conjecture is that that's an if and only if condition, but no idea where to go from there. So thank you very much. While you're thinking.
No questions, no comments?
Nice talk.
Thank you.
right, so let's thank Scott again. Let me suggest we have 8 minutes break according to this clause.
Do you want me to stop? Do you want me to stop the recording?